AP classes or AP calculus specifically in the past, you do get questions like this, right? Thank God it's not like 45 questions where it's all conceptual, right? There's a lot of computational stuff too, but these will definitely show up. Anyway. All right, let's take a look here at our next section, 3.2. So MVT, mean value theorem. For those that had AB last year, the mean value theorem was the speed trap project, kind of the intro we did to that. And so we're going to jump in. We're going to do 3 examples here. And some of these are going to be maybe a little deeper than they appear at first. There's going to be some work that needs to go into these for these to make a lot of sense. And so let's take a look here at example 1. It says, if f of x equals that piecewise, kind of a mess looking, but I mean, it's not that bad. Determine whether the mean value theorem can be applied to f on the closed interval 0 to 2 pi. So this is implying that there's a condition, right? Or perhaps conditions. So what would say, or what would determine that the mean value theorem can't even be applied? Or could be applied? What are the conditions we're looking at? Go ahead, Johnny. Continuity and differentiability. So technically, it's continuity on the closed interval and differentiability on the open interval. And so we have to figure out, are either one or both of those true or false? Because if one of them is false, then you can't apply the MVT. If they're both true, then you can. And so we need to figure that out. So I don't know how much you guys have done already with this. I've noticed some folks kind of jumping in. Let's try to confirm continuity first. That's usually where we start. That's usually the easier of the two to handle. Do you remember if you're trying to prove that something is or isn't continuous, what do you have to start with? There's a kind of a certain type of statement you got to... Limits, right? And specifically one-sided limits, right? Limit from the left and limit from the right, and then the value of the function at that point. We need to confirm. So, or deny. Let's confirm or deny that f is actually continuous on the interval 0 to 2 pi. Usually where I start off with these is look at the two pieces. I mean, you look at the top piece is just a parabola, right? And so that's continuous and differentiable everywhere. Bottom piece is just, it's a little bit messed with, but it's just sort of a normal sine function. It's been shifted up a little bit, swished down somewhat. And that's continuous and differentiable everywhere. So isn't the issue the joining point? Pi. So this is either going to work or not work based on what's happening at pi. So take a minute, see if you can confirm continuity. And if we can confirm continuity, then we'll move on to differentiability. We're going to be really, focus on kind of the symbology and your fluency with the notation and how it works. And the last thing I want you to do is be like, that one thing with the stuff, like it equals the other stuff with the other thing, right? Yeah, I mean, we're good. Wholly clear? Yeah, I totally understand. Yeah, we're just like, right there. It's as if I was writing a textbook, right? So we'd rather use some good notation and have it make sense to anyone who's reading it. Did you get my joke that I sent you? Yeah. Okay. Yeah, I did. That's why I did. I sent you. I thought a funny joke. Funny in the math, right? That was my name on my fantasy football team. I'm number -e to the I didn't. Didn't work. Okay. Let me do a little work here. Let's see if this makes sense to you guys. I'll try to give you a good example of some notational fluency here. If I'm trying to determine if this function really is continuous, continuity, there we go. I'm going to start off with this statement right here. Limit as x approaches pi from the left of f of x possibly equals the limit as x approaches pi from the right of f of x, and that possibly equals f of pi. Does that statement look familiar? So if you're trying to prove continuity or disprove continuity, you've got to start there. Anything having to do with continuity that you got to show your work, we're going to start right there. Okay, so from the left, we're talking about the parabola, right? So anytime you're trying to do a limit, I always think of the whole direct substitution thing as an option. And so I'm going to try that. And if I just plug the pi directly into that left-hand piece, I think it's going to work out pretty nicely. It'd be 1 over pi times pi squared. So that would be pi plus 2 is maybe equal to The right side, it would be sine of 2 pi, and that's just 0. So 0 plus pi plus 2. Look at that. And that's also equal to f of pi because f of pi was contained within the sine part of this piecewise. So since all those things are equal to each other, what does that mean? It's continuous, yes. So continuity, check. So far so good. It would be a mistake to assume then that continuity implies differentiability. Isn't that backwards? Differentiability means that it's also continuous. Continuity doesn't mean differentiability. So let's check out differentiability. And in order to do that, I am going to find a derivative. So for diff, f prime equals, what would be f prime for the left piece, the one on top there? 2 over pi times x. And that is if x is less than pi. And then how about the other piece?
2 cosine 2x.
2 cosine 2x. And of course, pi is a constant, 2 is a constant, so both of those derivatives are 0. Bless you. Isn't it kind of tempting sometimes to think of pi as not being a constant? Because it doesn't look like a 9 or whatever, but it is a constant. So it just has a derivative of 0. So this is if x is bigger than pi. Okay, so now I'm going to decide, we've already determined continuity, and so I'm going to see if differentiability works. So from the left, I'm going to say 2 over pi times pi possibly equals 2 cosine of 2 pi. How's it all work out? Those cancel. What's 2 cosine of 2 pi? Oh my gosh. It worked. Who knew? Isn't that amazing? So differentiability, did you guys get the same thing I did? Differentiability and continuity, that means the MVT can be applied. We just proved it. And awesome. So we got to confirm these conditions. And so let me just pause for a second before we finish this off. It's really important for us to realize that whenever you are using the MVT or the other one, the IVT, that you confirm the conditions being true, and not only that, that you are for certain that you've written it down, right? Don't just think about it, write it down. Yeah, Brandon.
For a problem like this, would it be viable to just prove the differentiability first and then save a step and not do continuity if it is?
Yeah. Differentiability implies continuity, but if you're going to use the MVT, you have to mention both.
Okay.
They are huge sticklers. So it used to be like 2 years ago at the reading, if you just used the MVT, they're like, oh, they used it. They must have assumed correctly that the conditions were met. Now they don't want to just see one of the conditions. They want to see both of them written down. So they've become far more sticklerish.
You could just prove that it's differentiable and then just write
And say, hey, differentiability means that it's also continuous, therefore I'm moving forward. Yeah, that's fine too. Okay, so we've proved that the MVT can be applied, and so now we're going to try to find all the values of C in the open interval 0 to 2 pi, so that f prime of C equals f of 2 pi minus f of 0 over 2 pi. So I don't know if you guys have enough room with the size of this. I think I'm going to erase this stuff. Is that okay with you? Do you have written down what you need to write down? Okay. So let me just get rid of that and go back to this. Okay, so this is essentially the hypothesis of the mean value theorem. And I'll say it in these words. I think I said this somewhere in the video probably, that if you know the average rate of change, which is what this is, then you know for sure that the function you're dealing with has an instantaneous rate of change somewhere on the interval, as long as the function is differentiable and continuous on your interval. So I think I'm going to go ahead, I guess I'll go back. Maybe I should not have erased this. I'm going to go ahead and write down f prime real quick. F prime was 2 over pi x for the left interval and 2 cosine of 2x for the right interval. But in order to use that, we need to figure out the average rate of change. So I'm going to write this down, f of 2 pi minus f of 0 over 2 pi minus 0. So if I'm going to plug in a 2 pi, into which piece do I plug the 2 pi? The bottom one, right? Because that's the domain that actually has that 2 pi. So it's going to be sine of 2 times 2 pi, so it'd be sine of 4 pi, plus pi plus 2, minus f of 0. Where would the 0 go? Into which piece? First one. Right? Again, the domains match up. So 1 over pi times 0, which is 0 plus 2 is 2. So I end up with this all over 2 pi. And let's see here, sine of 4 pi would end up being what? 0 plus pi plus 2 minus 2 just ends up being pi. And pi over 2 pi is 1/2. So our average rate of change on this interval, isn't that amazing how math works out sometimes? I mean, that piecewise looks ugly. Figure out this average rate of change, it's actually not that bad. It's 1/2. You would have probably thought it was something totally worse than that. Okay, so then to finish this off, I'm going to set that 1 over 2 equal to my 2 derivative pieces and decide where this coinciding of the average rate of change and the instantaneous rate of change happens. So I will write 1 over 2 equals 2 over pi x. So give me, it looks like it's just going to be 1 point. How would I solve this? I hate to ask, but I know that I probably should. Divide by 2 over pi, which is the same thing as? Multiplying by pi over 2. Yep. So if I do this and this, I end up with pi over 4 is equal to x. And if I had $1 every time a BC calculus student said, man, I totally get the calculus, but my algebra, those darn fractions or something like that, right? I mean, it happens to all of us too many times, more times than we'd like to admit. Okay, then the other one would be saying 1/2 is equal to 2 cosine of 2x. And this, I think, is going to be calculator territory. You divide both sides by 2. So you get 1/4 is equal to cosine of 2x. Do the inverse cosine of both sides, divide by 2. Yeah? This come out to be some decimal, I'm sure. Anybody have it? X equals...
I got 3.801 and 5.624.
5.624. And both of those do fit within the domain, so
Yes, and
logical.
check out.
Okay. Anybody have a confirmation on that? Josh usually didn't make too many mistakes, but, In Josh we trust, huh? Oh, no, Jasmine doesn't. I like that, Jasmine. Jeff is going to check. Jordan, did you check?
Yeah.
Okay. So we're good, you think? Pretty solid. Any questions? It's a pretty complex question, wasn't it? There's a lot going on. And this is only your second day of doing math in school in a while, so give you some time and space to, ask any questions. Especially for our friends Jeff, Jaden. I hope you all feel supported here. You're in a classroom full of accomplished mathematicians, and hopefully they're leading you the right way. Hopefully Colin's not feeding you bad information back there, because I can see him doing that just for fun. Okay. Hey guys, we solid? Y'all look solid. Okay, moving on then. Let's see here. Maybe these others aren't quite as complicated. I don't know. We'll see. So example number 2, this is one part of the infamous wind chill problem that comes up from time to time. I think last year in AB we did one part. This is a different part, so whatever. Wind chill is the temperature in degrees Fahrenheit a human feels based on the air temperature. In Colorado, we know all about that. And the wind velocity V in miles per hour factors in as well. If the air temperature is 32 degrees Fahrenheit, then the wind chill function is given by W of V, and the domain is 5 to 60. So the question here says, find the average rate of change of W over the interval 5 to 60. So that's one thing we're supposed to do. Once we've done that, we'll do something else having to do with instantaneous rate of change. So if you wouldn't mind, take just a moment. Definitely calculator active here. Take a moment and figure out what that average rate of change of W is. I'm going to let you write that out. Oh, thank God for lids, right? There's like $700 in electronics just waiting to die.
I don't know though, I feel like no lid would be a little bit more fun.
It would be more entertaining, no
Yeah.
doubt. No doubt about that. I say this as the husband of like a dedicated anti-lid person. My wife is like so anti-lid.
I'm anti-lid.
It'll have like a lid, a really nice lid like that, and she'll just leave it off. And I'm like, oh, my computer is right there.
That's what I do.
Oh, it drives me nuts. Oh, man. No, I like straws. I go with straws. Yeah. This is all sealed up. I know that no one has been playing around with it. But somebody might have been playing with the edge of the cup. Don't you think?
No.
Oh, okay. Well, that sort of thing is on my mind sometimes.
Yeah.
I had friends that worked in restaurants, and I'm like,
I'm not a germaphobe.
I'm not really either. It's just like straws, like stuff that
It's like a 5-hour rule for me now.
5 hour.
Yeah.
If it's been 5 hours, it's probably, bacteria is probably like flown off or whatever. Yeah, okay. Or maybe it's been multiplying this whole time, and now there's like 10 billion of them instead of just like 100. I think that's the more likely scenario. Maybe it's not all good protein, right? I guess DNA is protein, but it's not all good. Could be bad. All right, so average rate of change would be this. W of 60 minus W of 5, all divided by 60 minus 5. Standard protocol would be for you to write this down. So it strongly suggests you do this. It's not always the case, but for my quizzes or tests or AP readers off in the future, sometimes this step is actually associated with a point. And not having it might actually take away a point. So we want to see what you're thinking. We don't want to just see this number magically appear, and it's really tempting to do that when the calculator is active. Again, I encourage you to write this down. Has anybody taken this through with the calculator and done W60 minus W5 over 60 minus 5? Jack, what'd you get?
0.254.
So 0.254. Do you guys agree with Jack? Negative?
How? How is your calculator not showing this? Oh, you reversed it, never mind.
You just do it backwards?
I did it backwards.
Okay, gotcha. So we agree that that should be a negative number?
Yeah.
Okay, so negative 0.254, that is the average rate of change. And then it goes on to say, once you found that, find the value of V for which that instantaneous rate of change of W is equal to the average rate of change that we just found. So this is where we are going to set this negative 0.254 equal to the derivative of W of V. So this would equal, well, the derivative of 55.6 is 0. What's negative 22.1 times 0.16? It's got to be like 3 something. Negative 3.536 V to the negative 0.84. Make sense? So I've set the average rate of change equal to the instantaneous rate of change. And now would be where you probably turn to a calculator to figure out what the solution to that equation is. You could graph it. You could do the negative 0.84th root, I suppose. I don't know. Graphing's probably a little bit easier. But your option there. Anybody have an answer to this equation?
Yeah,
20?
23.011. You rounded.
So it's 23.011.
23.011. What might be the units that would go with something like that? Miles per hour is right. So how you guys feeling? Is this this one wrapped up pretty nicely? We're ready to turn this one in for grading. Brandon? Brandon says maybe no. Or question?
On this one, why don't we have to prove continuity?
Oh, that's the question, right? So maybe we aren't ready to wrap this up and turn it in. Right? So let's talk about the scenario here. In example number 1, it was explicitly told to us to prove that the MVT really applies. Here, there was no mention of the MVT anywhere, was there? I mean, kind of the hypothesis was there, find where the instantaneous rate of change and the average rate of change are equal. But it didn't come right out and say, use the MVT. Kind of had to. And so we did use the hypothesis, the NVT, we used it right here, but nowhere did we say anything about continuity and differentiability. So here's where you kind of play the test game a little bit. If it doesn't explicitly say you need to prove this, then all you have to really do is positively identify it as being continuous and differentiable. And you could use some tools at your disposal. I mean, the fact that it's v to the 0.16 and we don't have any negative inputs means that we're not going to have any issues with domain. There's no vertical asymptotes. There's no removable discontinuities. So I think we do have a nice continuous function. There's no, I don't think there's any issues with differentiability. So we just would mention it, right? So we'd say, because W is continuous and differentiable on the interval 5 to 60. The MVT applies, I suppose you could say, and then we obviously went on to use the MVT. You don't actually have to name the MVT anywhere in there. You can use the hypothesis. I think it's a good practice to do that. If you basically work the hypothesis and state that the conditions were met, then I think we're good. Okay. I was hoping somebody would say, wait, what about this? Good. Any questions? So in that little course agreement thing that some of you have signed and turned in, and by the way, if you have it signed and you didn't turn it in, don't forget to do that today. You can do it tomorrow as well. In there I mentioned something about, I really want you guys to become good, great, strong mathematicians, not just students who memorize stuff and hurriedly kind of cram things in your brain at the expense of understanding and conceptual grasp. And so that's what this is all about. So when I ask those kinds of questions, if it seems like I'm forgetting something, or maybe I'm setting you up like I was that time, sometimes I just forget, don't hesitate, right? We want that understanding. We want you to ask those questions. You might be right on something, you might be wrong on something. It doesn't really matter. Just want you to keep asking until we get to where we want to go and you're satisfied. So, okay, so we're good? Let's move on to, I think, what is the last one here. In this section, and that would be example number 3. Okay, here we go. The mean value theorem does not apply to the function f of x equals x to the 2/3 on the interval -2 to 5 for which of the following reasons? Let's make this a no calculator. I don't know how much the calculator would, maybe it'd help you a little bit. Let's make this a no calculator and see what you can come up with for this one. Let's check this one out. Mean value theorem does not apply to f of x on the interval -2 to 5 for which of the following reasons. Kind of like we did before, let's just vote. What do you guys think about A? Is A the correct answer?
No.
Nobody likes A. All right. So we're just going to cross out A. How about B? F of x is not continuous on that interval? What do you guys think about that? Is that the right answer? Question? No, or are you just gesturing?
I'm just,
Okay. Just had to ask. All right. C. F prime of -1 does not exist. F prime of -1 does exist?
Yes.
It's tempting, right? But you still get an odd root, don't you?
Yeah.
And so you can plug a negative into an odd root, and that's okay. So I agree. C. If we eliminate some of these, and in your mind you're like, whoa, I wasn't so sure that was wrong, say something. It's totally okay. All right. F of x is not defined for negative numbers. Again, this is kind of getting at the odd root again, isn't it? It's tempting to look at it and be like, hey, it's a root. Oh, we can't do that, but it's an odd root, so you could do that. So we're left with E. F prime of 0 does not exist, and you guys think that it's that?
Yes.
What's going on at E? Yeah, 0 on the denominator. Yep. What else could you describe it?
There's a negative on the denominator.
There's nothing wrong with the negative in a denominator.
Oh, yeah.
0 is a problem. There's something else you could use to describe this. On the graph. Yeah, but on the graph, what does it look like? The sharp point, right? Or remember what that one kid called it? This was still joked about this year at the reading. The doink point, yes. Doink point. So for those that didn't have me last year, at the reading 2 years ago, there was a point of non-differentiability on some graph, and they had to justify that it was not differentiable. And so they listed out all the things that a student could call it, and it would be okay. Like they were okay with sharp point, corner, some descriptions like that. But then there was a lot of them. They got to the end, they're like, one of the ones we won't accept is doink point. And somebody had done that. And I really don't think it was the student's fault. I think that, like I mentioned last year, I think the teacher was like, and the graph is going along, and doink, something like that. And that's the thing that stuck, right? So a lesson to you guys as you get older and maybe become parents, sometimes the thing that you intend for the person to really grasp a hold of is not what they grasp a hold of. They grasp a hold of the one thing that to you wasn't a big deal. So I'm always trying to be mindful of that. So I figured with this one, if I joke about it, maybe you'd remember that it was sort of a bad answer. So don't say that. So anyways, that is roughly what the graph looks like, right? Yeah? Oh my gosh. Look at all the work I did while it was frozen. You ready? I crossed out a bunch of stuff. Sorry. If I ever freeze it, just tell me. It's okay. I'm not going to be offended. Okay, so the answer was E, for sure. All right, do you guys have any questions at all? Yes, sir.
If I wrote the point of doink, could I right after?
No, I'm going to mark it wrong with a really large red X. I'm going to scratch it into your paper, physically. I'll get out even a marker. I'll be like, don't do that. All right. Hey, let's do this. Why don't I potentially save you a few minutes? Intro video people. You can see that there's an intro video starting here, but we've got about 7 or 8 minutes left in our class, I believe. I think we go to 25. And I'll just motor on ahead here. Maybe this will save you a few minutes if we get through this. So we just did section 3.2. This is section 3.3, which deals with how to describe functions that are increasing or decreasing, as well as finding mins, maxes using what's called the first derivative test. So down below here on this line, you'll see a statement, a couple of statements said is if f is continuous and differentiable, and if f prime is positive for all x in AB, then f is increasing. And a quick way to say this is if f prime is positive, then f is increasing. And we can talk a little bit about why that would be. What is f prime describing about f? The slope. So when you see this, f prime being greater than 0, you could substitute the word slope right there. Slope of f. So if the slope of f is positive, then f is increasing. And all of a sudden it makes a little more sense, right? So if the slope of f is positive, then f is increasing. But I'm going to make it a practice to say this. This is what we want to say, but that's kind of the reasoning behind it. So then, of course, if you have the same conditions and f prime is negative on the interval, then f is, bless you, decreasing. Quick way to say it, if f prime is negative, then f is decreasing. So just as a public service to our friends Jeff and Jaden, AB people, maybe you remember this. This is kind of the first of kind of some if-thens, right? If f prime is positive, then f is increasing. And there's a bunch of other if-thens. And now correct me if I'm wrong, at the start it seems sort of easy, right? You're like, oh, well, that's going to take no effort at all. But then you add another one, and it talks about some of the same kind of stuff. And then you add another one, and same thing, and then another one, and another one, and all of a sudden you're like, what started out to be really, really easy, you're like, I can't remember what f double prime means in regards to f or f prime and concavity and increasing or max or min, and you're all messed up. So take some time, write these down. I do have plenty of other resources for you if you do get mixed up, but Jaden, Jeff, for sure. Like these guys, maybe you're a tiny bit rusty, but I bet you they'll pick it up again pretty quick. For you guys, Jaden, seriously be very purposeful, Jeff, as far as like making sure that you don't in your head say, well, okay, well, if it's positive, it's increasing. That's not a federal crime. That's just a local crime, but it will get you some punishment, right? If you use the word it a lot or really at all, you say, hey, it's positive because it's increasing. We're all going to be like, what are you talking about? We don't know what it is. Okay, so, as far as looking at this on a graph, if I drew a graph of f right here, maybe the graph of f looks maybe like an exponential. Yes, ma'am?
Could you just go over why you have parentheses versus brackets on the intervals?
Good question. Believe it or not, so there's this AP teacher forum, online, that only AP teachers, if you have the code that you can get in and all this chit chat. And your question is probably the number one question asked by teachers on this little community forum. And it's been asked so many times, there's almost a canned response about this. So it really depends on your definition of increasing. So increasing can really, truly only be judged between 2 points. If I told you that my height increased, which it's not going to, but if it did, then wouldn't you want to know how tall I was yesterday and now how tall I am now? And then you could compare and be like, yeah, you're 1 millimeter taller today or whatever. So you've got to have 2 data points to compare. And so when you think about this, if f prime is positive on this open interval, isn't this closed interval only 1 point bigger here and there? And so if f prime is positive the whole time, then that 1 extra point on the end certainly won't make it decreasing now, even if the actual value of y at b is the same as the point one infinitesimally small distance to the left of it. Between those 2 points, it's still increasing on the whole interval. So, like I said, as far as I'm concerned, I'm not going to judge you on that. I'm not going to be like, sorry, Liz, you used a bracket instead of a parentheses or vice versa, so -1. And that actually is the College Board's position as well. There's enough arguing about it. In fact, you'll see, if I could show you, teachers getting into little math fights about it. No, I think it should be an open interval, and here's why, and they'll write this whole thing. And somebody else, some college professor, there's one guy at Metro that he'll get in, and he'll be like, no, it's this, and he has this whole paper on it, and it's a math fight. If you turned it into a physical fight, we'd see some big old punches and kicks, and just in the math world. So, but I think it's pretty well accepted by those in the know that it's this way.
Yeah, and you could have A and B could be those critical points. So it doesn't,
Possibly.
it doesn't matter.
Still increasing all the way up to the end, right? Yeah.
Okay, cool. Thanks.
You're very welcome. Okay, and then I think there's one more little piece of info here. Oh, yeah. And this kind of gets to Liz's question a little bit. The converse of a statement is just the switcheroo, you switch the ordering, is not necessarily true. Can you think of a counterexample to either? I know we only have a minute and a half. Sorry, this maybe is more of a 5-minute question, but. So in other words, hey guys, let me tell you what you shouldn't say. You shouldn't say, hey, f is increasing on a certain interval, therefore f prime is always positive. You can find a function that is always increasing for all real values, yet f prime is not always positive. Can we think of one of them? Say again? I'm not really talking about concavity, but concavity does play into it, for sure. It definitely does. Say again? Nice, Dylan. Well done. So this graph right here, y equals x cubed, comes in like this and does that. So if you find the derivative of x cubed, you get 3x squared, right? And at 0, the value of 3x squared is 0. So right there at the origin, f prime of 0 equals 0. So for one lousy point, f prime is 0. But for every other point on that graph, f prime is something positive, right? Yet, this graph right here would be considered to be increasing for all real values of x. And so this is where the converse simply isn't true. We can think of quite a few examples like this where you can't say that. And so don't flip it around. Say if f prime is positive, then f is increasing. That's okay, just not the other way around. Oh, whatever. Hey, love working with you guys. Have a great day. See you tomorrow. If you did not turn in the little course sign-up sheet, or the course agreement sheet, please do that. If not today, then tomorrow.